Hey everyone, so today we're starting Chapter 2, Unit 2.1 about using properties of exponents. Your warm-up is just to simplify each expression. Hopefully you remember a little bit about exponents and you can look at these and think to yourself, well, negative 2 to the third power means negative 2 times negative 2 times negative 2. And you can go ahead and finish that from there. And then the same thing with example number 2. So take a minute, do those problems on your own. Example number 1, we're going to look at today a couple different ways to simplify exponential rules, but just to give us a taste in the beginning, we have this problem, negative 4 times 2 to the 5th quantity squared. And when you simplify that down, you break it out, really what that means is that the squared is being applied to the negative 4 and to the 2 to the 5th. So I've got negative 4 squared, 2 to the 5th squared. And as I continue, I can go ahead and simplify even further and say negative 4 squared is 16 times 2 to the 5th and then squared again is actually 2 to the 10th. So 2 to the 10th is going to be 2 times 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 2. Right? So we've got 16 times 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2 is 256, times 2 is 512, times 2 is 1024. So then you have 16 times 1024. Go ahead and do your math out. And I'm getting 16,384 as an answer. So that's kind of the extreme. But what I really wanted was for you to be able to see that this is your simplified solution. The next example, 11 fifths over 11 eighths to the negative 1 power, tells us that that negative 1 is going to be applied to both the 5 and the 8. So there's an in-between step here that's not shown, and that's 11 to the negative 5 over 11 to the negative 8. And that's because 5 times negative 1 is negative 5, 8 times negative 1 is negative 8. When I have negative exponents, I want to switch their position in the fraction to make them positive. So 11 to the 8th over 11 to the 5th is what I get for an answer. I can move even further here and say 11 to the 8th over 11 to the 5th is really just 11 to the 3rd. And I can go ahead and solve that if I wanted, or I could leave it just like that. So we're going to go over some of those rules that we haven't seen in a long time. And those are the product rule. Oops. The power rule. Powers of product, which is a little different. Negatives. 0, quotient, and power of quotient. And we'll go through each of these just as a refresher to make sure that we remember all the different steps. There we go. So, for the product rule, what that basically says, if you have a number raised to the power and you multiply it by that same number raised to a different power, you're going to get that number with a power of the first plus the second. So 2 to the 4th times 2 to the 3rd would be 2 to the 7th. The power rule shows us that a number raised to a power and then raised to a second power is equal to that number with the power of the first times the second. Powers of product. If I have a product of two numbers, a times b, and it's raised to a power, I know that each a and b are raised to that power. Negative powers, I want to be able to flip that to a denominator or to the opposite of wherever it is, and that will make it positive. I don't want any negative powers in my examples when I'm done simplifying. I want them all to be positive. Zero power, a to the 0 is just equal to 1. Any number to the 0 power is always equal to 1. Quotients is that subtraction rule that we just looked at in example 1. And the power of quotients basically says if that an entire quotient, like a fraction, is set to a power, then that means the numerator is raised to that power and the denominator is raised to that power. So make sure you get all those rules down. If you want to work out some examples of those, feel free, right? We said like 2 to the 3rd times 2 to the 4th is 2 to the 7th, but 2 to the 3rd and then the 4th is actually 2 to the 12th, right? So you got to go through and see some examples and make sure that all those rules are really working for you. The other part of this unit that we need to go over is scientific notation. And some of you should have seen scientific notation in Algebra 1, but just to make sure, scientific notation basically lets us take the amount of zeros after a number and simplify it down to the value 10 to a particular power. So this example says a swarm of locusts may contain as many as 85 million locusts per square kilometer and cover an area of 1,200 square kilometers. How many locusts are in such a swarm? So this is a basic area problem. It's 85 million times 1,200. Now, we could plug this into the calculator, we could just multiply in our heads or figure it out, or we could write this in scientific notation, which would be 8.5 times 10 to the 7th power times 1.2 times 10 to the 3rd power. And that's because I'm going to get rid of all of the digits except the very first digit, and then I'm going to put my decimal place, and then however many other digits are following that first digit that are not equal to 0. So in this case, I took 85 million and then I changed it to 8.5, and I'm multiplying it by 10 to the 7th power because in order to get back to that 85 million, I would have to go 7 spaces to the right. So now that I have this equation right now, I can rearrange it and say 8.5 times 1.2, and then times 10 to the 7th times 10 to the 3rd. Well, 8.5 times 1.2 is 10.2, and 10 to the 7th times 10 to the 3rd, following our product rule, is going to be 10 to the 10th power. But this 10.2 is not completely in scientific notation. So in order to rewrite that, I need to say 1.02, now that's in scientific notation, times 10 to the 11th power, because I moved an extra decimal place over to the left, so I need to account for it in my exponent in my scientific notation. So my solution is 1.02 times 10 to the 11th power, or 1.02, and since this was where my decimal point was, that's where I'm going to start counting digits. 0 is the first digit, 2 is the second digit, and now I need the remaining zeros to get me to 11 digits. So 3, 4, 5, 6, 7, 8, 9, 10, 11, and I can go back and add in my digit markers. So this is actually 102 billion locusts would be in that amount of swarm. But again, like I said, either answer this or this would be correct. You may want to check your work and think about, is this a reasonable amount of locusts? It looks like it probably is, looking at the photograph right here. So I would say yes. Example 3 is just simplifying. We're going to use some of those rules that we talked about. In this case, we do have the product rule in part A. The product rule says we just take the same base number and we add all the exponents together to get our new base. So B, negative 4 plus 6 plus 7 is going to be to the 9th. See? It's not too complicated. The second example uses the power of quotients and then also the negative rules. So first of all, the power of quotients, because I need that negative 3 to be accounted for. So now I have r to the negative 2 and then to the negative third. And then I have s to the third and then the negative third. So when I combine a power of a power, I multiply. So r to the negative 2 to the negative 3 is r to the 6th. S to the 3 to the negative 3 is s to the negative 9. And now that I have a negative power in my denominator, that needs to be moved up to my numerator. So my answer is r to the 6th times s to the 9th. The last example again has some of those negative powers there, so I want to be able to move them around. I'm actually going to look at my whole numbers and simplify. 16 divided by 2 is 8. N needs to go to the numerator anyways because it's negative. So I have m to the 4th, n to the negative 5, and then again to the negative 5. Now, I'm subtracting negative 5 because I'm using the quotient rule that if there's a number raised to a power over that same number raised to a power, I subtract the power from the denominator from the power from the numerator. So a little better English here. I have two n's, n to the negative 5 over n to the negative 5. So when I simplify that, I use the quotient rule. N to the negative 5 minus negative 5 is going to give me the new power for that. So right now I have 8m to the 4th, n, negative 5, minus a negative is actually a plus. So that's n to the 0. So I simplify down to just 8m to the 4th, because my 0 power says n to the 0 power is just equal to 1. 1 times anything is itself, so I don't even have to write that down. So that example used a lot of different rules. Example 4 is our last example. We're going to look at a power of a power rule. So our numerator here, x to the negative 3, y to the 3rd, all squared, over x to the 5th, y to the 6th. This turns into x to the negative 3 to the 2 and y to the 3 to the 2. And then when I multiply my powers of powers, I get x to the negative 6, y to the 6th over x to the 5th, y to the 6th. Y to the 6th over y to the 6th just cancels out. X to the negative 6 needs to be moved to the denominator to get rid of that negative. So I get 1 over x to the 6th, x to the 5th, which is the same as 1 over x to the 11th power. So we're going to practice simplifying exponential functions next week. However, make sure you do your daily homework quiz.